There we go. All right. All right. So so we have the relationship with the magnetic field. So del cross B equals mu naught times J, where J is the current density. And we have del dot B is equal to 0. And with these, we can define some vector potential where the magnetic field at some position is equal to the curl of this vector potential. And last time we found that the way we can write the vector potential is mu naught over 4 pi times the integral of current density, position, e through x1. So in other words, in all of our integrals, we talk about the prime as being the source, and the non-prime as being where we're looking. Prime being source, non-prime where we're looking. Now I need to erase this because I wrote too big, but we're going to use it in a minute anyway. Okay. I'm going to use this in a minute. Actually, I don't know what I'll do.
Well, I changed it to the other.
But these are the equations from the last section that we're going to be referencing. So just keep those in mind. All right. Specifically, so let me rewrite this up here. So I have it. See how far back can I go? Oh, I can go all the way in the corner. And a sub x is mu naught over 4 pi over current sources. And d.
No, I mean, new computers don't usually come with or anything that comes with the trial, but like the one that I can get.
Now, this thing turns out to be a lot more of a mess than we might expect. I mean, it kind of looks like a mess anyway, because you got a vector here. This is a vector, so it's like a vector integral. So, in other words, if I were doing an x component here, then this would be the x component of the j. Y component would be the y component of the j. So something like that. So the components would have to line up. So I could kind of do each one if it's Cartesian. Of course, you don't usually have Cartesian. You usually use other ones. So yeah. So anyway, let's explore this thing that they kind of come up with in section 5.5, which is the vector potential of a magnetic induction for a circular current loop. So this is about as simple as you can get in terms of currents. You have a current in a circle. Current goes around a circle. That's it. Yeah. So the current is a circle of radius A, centered at the origin. And so they put the x and y axis here. So here's my x-axis. Here's the y-axis. You see these up here. So your current is in the xy plane, centered at the origin of radius A. So here's the circle. So if I were to just continue. Okay, so this distance is A. Sorry, that goes behind you. My 3D perspective drawing is incorrect. Okay, so this distance is A, so radius A, and so we have our dl here. So our phi prime. So here's our little current. Here's our little piece of current right here. So that's our little thing. And so instead of integrating over the current, we're going to do like we would for charges. And we're going to integrate over the distances. So what we need to do is instead of having this dj, we're going to have to write that in terms of our coordinate system. So in terms of r, theta, and phi, it's not too hard to write because the only j that we have is we have a phi. So there's current I flowing through this. So we have only j in the phi direction. That's the only j we have. And it's equal to this current I Okay. Now, remember where we put the current, is in the prime. So sine of theta prime times del of cosine of theta prime. This factor just basically, this is going to be 1 when this is 0. So when this is, so this is going to, yeah. So this sine of theta prime just makes a kind of scaling factor there. And then del of r, r prime minus a over a. Because we have to have all of our units correct. Okay? Or we can write the vectorial current density in terms of the phis as this. So J vector is minus J phi times sine of phi prime in the I hat direction plus J phi cosine of phi prime in the J hat direction. So we can write down for the I 3 components. And the geometry is cylindrical symmetric. So it's easier for us, just for convenience, to choose the observation point in the XZ plane. In other words, we choose the observation point, choose observation in the XZ plane. So that would be here. Because it doesn't matter what angle phi is, whatever angle phi you have, this is all symmetric. So whatever magnetic field we would get over here, that would be azimuthally symmetric. So we can actually pick this, and so we're actually pick the observation point that's easiest. And the reason why this XZ plane is the easiest is because the phi, where we're actually looking, this is the observation point now, everywhere in that plane is equal to 0. Phi prime isn't, because phi prime is where the current is, but our phi at least is equal to 0. Now we simply plug into the formula. Oh, this is great. All right, so here we go. Okay, so I'm going to use this. I'm going to say that A phi, so A phi, A in the phi direction of R and theta is equal to mu naught I over 4 pi. Sorry, mu naught over 4 pi. And let me just go ahead and write the rest of this in here. So I'm going to say mu naught over 4 pi. Okay, multiplied by the integral of r prime squared d r prime d omega prime, omega being the solid angle. So in other words, we're actually going to be integrating over a sphere. So in other words, this is a volume integral. So you might think that we're actually going to do a line integral here. Will turn out to be a line integral, but only because of all these delta functions that go in there. That's the only reason why this. So in general, this is a volume integral. This is an integral over all space, volume integral. Because in general, I could have j's everywhere. I could have j's all over the place. Okay, so I write that integrand there, and then I multiply by my j. And my j is I over A. So I over A. Multiply by my sine theta prime del cos theta prime del of r prime minus A over, well, I already put the over A. Okay. Oh, so over, sorry. x minus x prime. All right, so now we got to use this. So we're going to use x minus x prime equals
I'm sorry, Professor, what is that last delta?
r prime minus a,
R prime minus A, thank you.
r prime minus a, yes. So this is equal to r squared minus plus r prime squared minus 2r prime multiplied by cos theta prime plus sine theta prime cos phi prime, but in this case it's just cos phi prime because phi is 0, so that makes cos phi of equal to 1. And so we get this slight simplification. We get to get rid of some of it. Not much of it, but we get to get rid of some of that. Now there is a couple simplifications we do have here. So when we put this in, we're going to do the r and the theta integrals when we put it in. So Jackson does this all at once. All right. So first of all, he does the r and theta integrals all at once. I'm sorry, the r prime and theta prime integrals in here at once. So what happens when he puts the r prime integral in there? So when we integrate over the r prime, then what that does is that puts all the r primes in whatever formula that's going to be equal to a. So every r prime in this formula and that one up there has to be replaced with an a. Not the r's, but the r primes. The other thing that we do is there's that integral over thetas that we have. And when we take the integrals over theta, same thing happens except for we replace all cosine thetas with 0. So cosine of regular theta equals 0. Sine of regular theta equals 1. I'm sorry, theta prime. Sorry. Cosine theta prime equals 0. Cosine theta prime equals 1. When you do all of that, then we get the numbers that he shows. So what we get for our a sub phi, so we have a phi of r and theta. First of all, I'm gonna pull that I over a out. So mu naught I over 4 pi a. So there's that. All right. The r prime equals a. That's this r prime here is a. That can come out of the integral, so I get another factor of a squared here. This sine of theta prime is 1. The sine of theta prime is 1, so that's going to be 1. So this is going to be 1. This is going to be 0, and this is going to be 1. This is going to be an a, but I can't take it out because it's attached to all these primes. So is that one. So what I end up getting is, let's see, what this top part is just I already plugged those in. That's it. That's it. There's nothing there. So it's just an integral, and the only thing that I have is a. Where did it go? I forgot to write something down, didn't I? Where'd it go? I forgot. Sorry. I've got a factor up here. I was going to lose my factor. So this is sine of theta prime. This is cosine of phi prime. There we go. So this one goes to 1. I still have that cosine of phi. That's the only thing left in the numerator. Okay, cosine of phi prime. Okay, so my integral, I've essentially done the first two integrals, so I just have 0 to 2 pi d phi prime. And then over here, I have cosine of phi prime divided by this. A squared plus r squared minus 2ar cosine of phi prime to the 1/2 power. All right, so let's see what Jackson says about this. Jackson says, this integral can be expressed in terms of the complete elliptic integrals k and e. Oh, isn't that exciting? Yuck. Okay, so let's assume that we knew what those are. I'm going to skip it completely because you know what? You can look them up if you need them. All right, so apparently there's elliptic integrals that deal with this thing where we got the cos phi, d phi, and a cos phi down here to the 1/2 power. And it really isn't just craziness, so don't worry about it. Don't worry about it. That's not what we're worried about here, okay? So here the actual result is going to be more than the integration, how to do the integral. Because this is a math class, and I definitely don't have time to teach you that, especially since I don't really know it myself. I mean, I don't remember these things. So what ends up happening is this. We can write this down, and I'm going to write the first couple terms of this A phi we have. So A phi first couple terms we get out of here. So I'm skipping down to 539. Okay, so I got mu naught. I got a bunch of crazy stuff here. A squared r sine of theta divided by 4 a squared plus r squared to the 3/2 power times 1 plus, now we get some other stuff, and the other stuff has more r's and more a's in it. So I got 15 a squared r squared sine squared of theta divided by 8 a squared plus r squared squared plus more stuff. Wow. Isn't that exciting? Isn't that just the best thing you've ever seen? Okay.
Quick, Professor,
Yes, go
just a quick question. The a squared in the top, should that have canceled to just a, or?
Which a squared where?
I've got my cursor on it, but you can't see that.
This one?
Yeah. Shouldn't that have gone to a because the a in the denominator before?
Oh, you mean this? No. This is after you do the integral. In
Oh,
other
okay,
words, I actually pretended that I actually did the integral for you, even though I didn't.
Okay, got it. Just
Yes.
checking.
So after you do the integral, you get, yeah. This is after you do the elliptical integral, and you get this weird thing. Okay, so. Okay, so this is my A, and this is my, so to get this written down or screenshot it or just look at the equation in Jackson, this is equation 539 in Jackson, all right? And that's the scary thing, because when we look at magnetic fields, right, when we look at magnetic fields, this is one of the simplest configurations you can get. It's a circle, it's a plated circle, center of the origin, with the current I flowing through it. You don't get much simpler than that. So then we take a look at the magnetic field. Okay, so what we have to do is we have to start looking up in Jackson because we have this A phi, which is not zero. So I have an A phi that's equal to stuff. Okay, stuff. Okay, it's the only component of A of the A vector because that's the only component of the J vector. So that was one nice thing. The only nice thing about this is that since J only had a phi component, A is only going to have a phi component. Okay, so there's only a phi component, but still it's a mess. So what you want to do is you want to look up curl in the back. So curl of that in spherical coordinates. Okay, so curl of vector A in spherical coordinates. In spherical coordinates. Okay. So when it says the E1 here, that means the R vector. So the R hat times, we only have a phi component. We only have a phi component, and the phi component in this case is the third one. So in other words, when we say the R is 1, theta is 2, and phi component is the third one. Okay? So the only one we have to go into that formula is A3. A3 is the only one. I don't know why Jackson put these 1, 2, 3s in there instead of your other ones, but that's it. So if I look at the R component here, I only have A3. That's all I have. So what I would have to do here is I say, okay, so it's 1 over R sine theta times dd theta sine theta of A3. That's it. Because I only have the A3. A2 is equal to 0, A1 is equal to 0. Then I have the theta component. The theta component, we want to look again at where the A3s are. And so the term that goes with that is the second one there. So minus 1 over R ddr of R multiplied by A3. There it is. So there's that. And then the phi component of the B vector. So this is the B. That's my magnetic induction vector. So my phi hat, well, the thing is if I look at my phi hat, this is a curl. So the phi is only going to have the other two components in it. It's only going to have the R component and the theta component when you take a curl. In other words, the curl is always going to be perpendicular to the vector that you're talking about. Since this is in the phi direction, the curl is always going to be perpendicular to the phi direction. So therefore, the phi component of it must be what? Guys need more coffee than I had. So curl of A is always perpendicular to the vector A. Okay? The vector A is only got a phi component. Okay? The vector A only has a phi component. The curl of A must be perpendicular to this. Must be. Just by definition of what the curl is. Since the curl of A must be perpendicular to that, the component of the curl must be what? 0. Since it has to be perpendicular. The only way to make B perpendicular, in other words, here, let me do this. This is BR, this is B theta, and this is B phi. Okay? This B has to be perpendicular to the A. Must be. Since A is in the phi direction, what must that component be?
0.
Has to be 0. You can't have a component along the A vector. There is no B in the phi direction. There's no B in the phi direction. The other way to see that is there is the current is always going to make magnetic fields perpendicular to it. This current flows in the phi direction. So it's going to make loops. It's going to make loops like this in the R and Z directions. You see what I mean? Oops, the other way. Sorry. Up on the inside, down on the outside. Okay? With nothing in the phi direction. Same thing for a long straight wire. For a long straight wire, current I, we would only have current is only in the z direction. Therefore, the A would only have a z component. Therefore, the magnetic field would have to be in the xy plane, i.e. circling around this, with no component along the current. That's how curls work. Okay? It's weird because when I look in my picture that in my recording, it shows this board backwards. So it's weird because I'm actually looking at a left-handed universe on my screen, even though on my board and in your lives, it's really right-handed. So yeah, so there is no phi component. There is no phi component. Now you might think, well, gee, but this thing doesn't really have all those different dependencies. But notice that even if A3 were constant, even if the vector potential were constant, that you would still get some BR in the R hat direction and B theta and theta hat, simply because you're taking that constant, you'd be multiplying by this, then taking a derivative. Up there, you'd be multiplying by sine and theta, then taking a derivative. So even if A3 were some constant number, if A3 were some constant number, you would still get magnetic field in those other directions, just none in a phi. All right, so turn back over here. So now we'll look to see what we have. All right, so I'm going to erase all of this stuff up here. And so what we do is we plug in our stuff, take these derivatives, and here's what we get. So we get the magnetic field in the R direction looks like this. VR equals mu naught I A squared cos theta divided by 2 A squared plus R squared to the 3/2 power multiplied by 1 plus that mess again. And this is actually almost the same mess that was before, except for there's a factor. So 15A squared R squared. So we got these other numbers here, and it's a mess, sine squared theta. So as you get more stuff over here for A squared plus R squared plus blah, blah, blah. I'm getting the blah, blah, blah on there, good. And then this one is even funner. So B theta is even funner. B theta is funner, so we get minus mu naught I A squared cos theta over 4 A squared plus R squared to the power. Now this one's kind of even funner because, oh sorry, this is 5/2 power because the integral is even weirder. So then what you get 2A squared here minus R squared plus, then you get a even bigger mess, 15 A squared R squared sine squared, oh Jesus squared, 4A squared minus 3R squared over A squared plus R squared plus blah, blah, blah. And you might think, oh, good grief, right? All right, so there's a couple of limits that we can look at here, a couple of them. Jackson only gives you one of them, but we can look at another one. If we look at the mess that we're having here, the big mess we have over here, we can look at what happens if this. So we can look at basically three places here, okay? So three limits to this we can actually look at and see, okay, kind of what it does. The first one is along the axis, along the z-axis, or near the z-axis, okay? So if we look at along the z-axis, then that means our theta is, so our cosine of theta is equal to 1, and sine of theta is equal to 0. Cosine of theta equals 1, sine of theta equals 0. So if we're along the axis, what happens is this. Okay, so if we're along the axis, basically, see all these terms with sine squared, blah, blah, blah in them? Sine squared, blah, blah, blah. Well, the sines is all 0. And since all the other terms have there's more signs in them, those all go to 0. So this is all goes away. This all goes away. Okay, so that's near the axis. So near the axis, we get something like that. Okay. And the cosine thetas would all be 1. And if we look at this right here, if we look at that, that's the formula that we kind of got before. So remember when we got that formula before with a circle? Well, actually, we didn't get it. But you could get it with a circular motion, just take it along the z-axis. Just directly solving using the Biot-Savart law. So that's along the axis. Another place to look would be near the center of the, near r equals 0. Well, if r equals 0, then the cosine theta isn't really going to matter here. So what you would end up getting at r equals 0 is you'd end up plugging r equals 0 in for these numbers. This would find out some p nonetheless. You plug in here. And so what you get is this. Erase all this stuff. Oh, now I forgot my where'd it go? It's fine, I'll find it. All right, so there it is. So a squared, this is 3/2 power. This is a little easier. So at r equals 0, our magnetic field points upward, and you basically get mu naught I over 2a. All right. Hooray. Okay. Well, those ones we could have actually kind of derived before, at the middle along the z-axis. And it's nice to know that this, indeed, this messy thing that we do does reduce to those things when we go back and we say, oh, okay, let's take this and go to 0, and take this and go to 1. But the only one that's really interesting, the only one that's really interesting to us, really interesting at all, or at least for this class, is this one. Now, the situation where we take r much, much greater than a. So once again, if we take r much, much greater than a, then the b sub r, then basically the idea is that whenever I'm adding the r squared and a squared, I can neglect the a squared in that. So we got mu naught I a squared cosine of theta, cosine of theta, and also we can neglect all the other terms because they are higher powers in a squared plus r squared. So a squared plus r squared, okay, goes to r squared, and anything with this in the denominator, since these are in the denominator, can be neglected. So neglected. So in other words, here we're also going to just keep that first term. We're only going to keep the first terms. Okay, so this these are equals this. Okay, so we're going to divide by 2 times a squared plus r squared, but it's just r squared now to the 3/2 power, which if we multiply this out, this would be r cubed. R cubed. All right. Yeah, b theta. B in the theta direction is this. Minus mu naught I a squared. Oh, I'm sorry, this is sine theta, not cos theta. Sorry. 4 a squared plus r squared, that's r squared to the 5/2 power. And now in this bracket out here, we have 2a squared minus r squared plus blah, blah, blah. If r is much, much greater than a, which term out of this thing dominates?
R.
The r. So then this just becomes r squared. I don't care if I am multiplying a squared by 2. This is nothing but negative r squared. There's a negative sign, right? Yes. So it's minus r squared. All right. So let's see what this is. This is mu naught I. R squared cancels most of those. So I get, so this is r squared to the 5/2, r squared to the 3/2 are r cubed. So then this is mu naught I a squared sine theta over 4 r cubed. Yeah. All right, so let's point to this one right here. So hopefully, did you guys have your coffee yet? You're at home, so you can get coffee, okay? Plenty of coffee here.
I'm out.
Huh?
Nothing.
No, you can't be out.
Yeah, sorry. Didn't mean to interrupt.
No. That's all right, we're gonna have to break it in to get it, okay? I just want to see if you guys can recognize it. So let me just kind of lump all that stuff in together. This mu naught I a squared to blah, blah, blah. That's just some constant, okay? I'll call it, I don't know, K or something, kappa, something like that. Some constant, mu naught I a squared and I get a cosine theta over r cubed, and that is my magnetic field in the r direction. Does this pattern look familiar to anybody? The cosine over r cubed.
Yes.
Ah, where'd you see it? What are we talking about? What does that thing look like? Let's see. Let's see.
Something from the the multipole expansion.
No, you're good. You're good. You got it.
Is it?
Yeah. Let me just point out where that
Dipole?
is, because I know we got it somewhere.
Is it a dipole or no?
Look at equation 412.
I don't have my book.
Oh, okay. So equation 412, those of you who have a book, looks like this. Here's the equation 412. So equation 412, if we look at 412 and 413, they have the dipole of the electric field. And so what you have with the dipole, you had E sub r is equal to 2p cos theta. So 2p cos theta, 2p cos theta over 4 pi epsilon naught r cubed, okay? And you had the E theta equals P sine theta over 4 pi epsilon naught r cubed. Oh. So notice, even with the extra factor of 2, even that extra factor of 2 comes in. In other words, the r component being twice the size of this component down here. So even that extra factor of 2. So in other words, this is completely analogous. This is completely analogous, except for this one has a different constant. And instead of the dipole moment, we've got some charge. So there's something here that's acting like kind of a dipole. So this circle here has a quantity that's acting like that electric dipole. So what we do is we're just going to define that. We say, okay, well, what this looks like is this. So we change up this up again. So let me rewrite these things. So this was a mu naught I mu naught over 4 pi mu naught I a squared over 4 pi. Oh, I forgot my pi's in this, didn't I? Oh, I know it. I know it. Okay. All right, so over 4 I a squared for sine theta over r cubed. Okay. So now we do a little trickeroony with this. Okay, so I'm going to pull this cosine theta over r cubed over here. So cos theta over r cubed. And I'm going to pull my sine theta over here. Go and pull this IA squared and put it in the middle. And multiply and divide by pi. Okay. Okay. Now we have our analogous little quantity here. So this quantity right here, that little quantity there, is our magnetic dipole moment of our loop. So we're going to define our magnetic dipole as this. So for that loop, that's our magnetic dipole. All right, let's take a break. See you back at 6:10. Okay. So now we're going to take a look at this, and we're going to kind of do the same thing we did with the electric field. Of course, it's all going to turn out to be a bit more complicated than the electric field, but still, it always helps to kind of use what we've always had before. So in this case, with our magnetic field, we're going to take some distribution here of localized current. So I have current in here, some localized current density. And I'm looking at the field. The point where I'm looking at the field is far, far away from this current. Far away from the current. So we have this direction from x vectors here. And all the prime vectors, all the x prime vectors would be in here. So here's where all the current is. The currents are all localized, so I'll call that J prime because it's localized to wherever x prime is. So x prime is always inside of this thing. So that's my x prime vector. So what we do is we start out with a localized current density. So we have localized current density. Current. Okay. So remember when we started doing the multiple expansion for electric fields, we talked about multiple about charges. Here we need talk about the currents. So we're going to use this expansion here. So we use the expansion of 1 over x minus x prime We use the expansion for x much, much bigger. I'm sorry. X much, much bigger than x prime. In other words, the size of the two vectors. So we get this. We get that this is equal to 1 over x plus x dot x prime over x cubed plus dot. And so what we can do now is we can go back to our old A formula. So I'm going to go back to the old A formula here. So the A looks like this. Okay, so I'm going to pull it up. Where do I put it? I'll just put it over here. So A of x, my mu naught over 4 pi, integral of j prime divided by x minus x prime. D3. So by putting this expansion in, I can pull out all these non-prime terms. And I can go back and I can say, what am I A? Now it looks like this. So I got A. So the formula here is for each component. So each component of A. The ith component of A is equal to this. So mu naught over 4 pi times. The first term looks like this. So it's 1 over x multiplied by the integral of the ith component of the j, d3x prime. Okay, plus x vector over x cubed dotted with, dotted with the integral of j sub I prime multiplied by x prime vector d3x prime plus dot dot dot. Now what we're going to do with this is we're going to have an identity that we're going to end up using to solve this. So we're going to write down that identity first. So this identity is weird. So basically the idea is that the j, as long as j is localized, so as long as j is localized, in general, so in general, j being localized, we would have something that looks like this. So we have f of x, so f prime and g prime are both functions, well-behaved functions of x prime. In a region. So then we have this identity that we're going to use. So we're going to use the integral of f, and I'm going to go ahead and write prime, j prime, dotted with, so j prime's a vector here, dotted with the gradient prime of the g prime. That's going to kind of be our first term. It's a little weird there, but that's our first term. Plus g prime multiplied by j vector, dotted with my gradient f, plus f times g, fg times the divergence of j. If I integrate that, I have to get 0. Let me pull this over. So that's my identity that I'm going to use. Now, all I have to do is choose an appropriate f and g. These are all primes. all I have to do is choose appropriate f and g, and then I can figure out what each of those terms are going to be, just by choosing an appropriate f and a g. All right, so for the first term in the sum, this 1 over x term right here, this term right here, we choose f equals 1. That's kind of a well-behaved function right there, right? F equals 1, okay? And we're going to choose g equal to x prime. G is equal to x sub I prime. All right, let's see what this gives us when I go to plug this in here. All right, so this first term, f prime, that's 1. So I have j prime dot the divergence of g prime. What this does is that this gradient is only going to be, so the gradient of g prime, the gradient prime of g prime is equal to 1 if the component, if you're talking about the I component. So it's all going to be equal to 1 times x sub I hat. Does everybody see that? Because g is x sub I. G is that component. Remember that this thing here is, so let me go ahead and write this out. So this is jx plus jy, sorry, jxx, jxx hat plus jy y hat plus jz z hat. I'll just do Cartesian z, okay? Dotted with this gradient of g. Well, if g is xi, okay, that's one of the 3 components. That's one of the 3 components. So whichever component that we are talking about, x, y, or z, that is the only one that's going to happen over here. So let's say in this case that this represented y, all right? And then we would be looking for the y component, y. So what you would get is this is just y hat vector, because my derivative in the y direction is 1, but that's only for the y hat. So that's why I'm going to replace my del G in general with x sub I hat, because I'm saying that this is one of the 3 components. Okay, so that's either going to be x, y, or z, and whichever one is, I'm picking that one out. I'm picking that one out. Well, if I look at this, what am I going to get with this dot product here? Uh-oh, people forgot their dot products. What's x dot y?
Okay.
0.
Michael, you mumbled something, but I didn't hear it. What's x dot y?
0.
It's 0. X dot y is 0. What about y dot y?
1.
Y dot y is what?
1.
You can type in chat. So y dot y is 1, and z dot y is 0. So all this does is it takes this component. Okay? So this whole thing here just becomes jy. Jy. Okay? So the effect of taking this as being xi makes this thing j sub I. That's it. There you go. That's j sub I. That's the ith component of the j. Okay? That's the ith component of the j. Does everybody see where I got that? That's the ith component of the j. Let me write this out more formally because remember that this has to deal with the x prime. Okay? We're going to want that in a minute. But that's the first term. That reduces to this. Let's look at this second term. What's the gradient of 1? Well, I'm taking derivatives, right? dx x hat, dy y hat, dd z hat, right? Well, it's 1.
So it's 0.
So 0. I'm taking derivatives of 1. It gets 0. This is 0. This one's a little tricky. Well, actually, it's not. So this f is 1. The g is xi. So this is xi. Okay? Multiplied by the divergence of j. Now, we're dealing with steady state currents here. Since we're dealing with steady state currents, there's no charge buildup. If there's no charge buildup, go back to the very first of this chapter, the divergence of j has to be what? Say it out loud, Sebastian. We can barely hear you.
Oh no, I'm like looking through the last lecture notes.
Ah, you're looking. All right.
If there's no charge buildup, you're saying what is the divergence?
Yeah, what is the divergence of the current density if there's no charge buildup? In other words, d rho dt is equal to 0.
Is it 0?
So this has to be 0. This is continuity.
Okay.
Okay, so this is 0. That's 0. Okay, so now let's see what this thing is telling us. This thing is telling us that the integral of ji of x sub I d3x prime, what does this tell me? This integral has to be what? Well, here's the equation. That's 0, that's 0. So what does that have to be?
Also 0.
It has to be 0. It must be 0. This has to be 0. That has to be, it can't be anything else. That term is right here. So I'm going to erase this. I don't want to erase my function, but I'm going to. Make sure you get this screenshotted and written down because I do need to erase it. Because it's going to be, well, okay, I'll just make it a mess. It's fine. That's this term right here. So notice what we just showed, that term right there is 0 for any localized charge, any localized charge distribution. That's 0. That's 0. The component of any component, this is any component of the vector potential will have that first term be 0. Now, let's go back to the electric field. What was the first term in the electric field expansion correspond to? The first term in that electric field expansion.
It was just total charge?
Just total charge. It was just the total charge. The monopole moment. Of course it's 0. There's no magnetic monopoles. It works. It's consistent. The first term in the magnetic, the first non-zero term in the magnetic field expansion is going to be your dipole term. There's no magnetic monopoles. It's great. Has to go somewhere. Charges have to go somewhere. So yeah. Okay, good. So at least this, all these fancy definitions, we better come up with something that's consistent with what we had before. All right. So now we got to figure out, okay. Well, I took care of the monopole term, so let me get rid of it. So here's our dipole term. Let me write it down. The dipole term looks like this. This is the one we're actually going to be looking at. So we've got this integral of x vector over x cubed, dotted with the result of this integral, which is also, by the way, a vector. So j sub I vector. No, j sub I, sorry. J sub I of x prime. Okay. Multiplied by, here's where the vector comes in. X vector prime. X prime. Oh, no. Okay, so now we get this weird thing. And we got to take care of it. All right. So let's come back to this idea again. So now what we're going to do is we're going to make a slightly different choice. So we're going to choose the x of I. So the f in this function is going to be one of the components. And the g is going to be a second one of the components. Now, this thing still has to go to 0. Okay, so that thing will still be 0, so we don't even need to worry about it because we're still going to be dealing with the divergence here equal to 0. So I'm not actually going to erase this. We only have to deal with these first two terms. All right, so this is x of I. This thing pulls out the g component of this. So this is jj. X of I, jj. If I go to the other term here, this is x of j. This is going to pull out the I component, ji. And so there we go. That's what we get. All right, so now what we got to do is we got to take this thing up here. We got to take this thing up here, and we got to write it out. We got to write it out so we can see if we can kind of get that combination going on, so we can make things equal 0. It'd be nice. So yeah, I'll go ahead and start this mess. All right. Okay, so let's take this thing. We want to take the part of it that's an integral. So we have the x dotted with this stuff. So we have integral of x prime multiplied by j sub I d3 x prime. And so what we're going to do here is I'm going to say, okay, for each, so I'm going to make this a summation here over j, because that's what the dot product is. So where I take this, I'm going to cycle through the j components here. So this is x sub xj integral of x prime j, j I, d3 x prime. Minus 1/2 for our fun double counting. Sum over j. So now what we're going to do is we're going to say, okay, sheesh, of xj multiplied by integral of x sub I prime jj minus x sub j prime ji. Where in this case we've actually used this because one of these is equal to the negative of the other. So this is equal to the negative of this, and this is equal to the negative of this. So if I were to put in negative xi jj here, then I would get 2 times xi jj, and that's where I get my factor of a half. So that's what I did there. So I used the fact that this, when we integrate this, this is equal to the negative of that. All right, so what we can then do is we can take this thing and we can do it. What does this thing look like? So I got ij minus ji. Ij minus ji. What's that thing kind of look like?
The delta function?
No. So let's say that I had a and b, and a and b are some kind of vectors, right? So I had ax by minus ay bx. What's that look like? I'm getting a little cross here.
Like the cross product?
Yes,
or-
like a cross product. See? Yeah, so that's a cross product. And in fact, this i's and j's here, that's the component in the third direction. That's the component in the third direction. So this, I can change to this. J's. Multiply by the component there in the third direction. Whee! So x prime cross with j in that third dimension k into x prime. And now there's one more thing that I need to do here because I need to fill this out because depending on what this is, depending on what this thing here, so we're going to change this here because we're going to add another sum in here because we want to sum over all the components. So we have a minus 1/2 here, sum over both j and k of this little thing here, epsilon I j k, x of j times this. Now, what's this thing? Epsilon I j k is equal to 0 if any two of ijk are equal. Positive 1 if ijk are cyclic. Negative 1 if ijk anticyclic. In other words, it's a shorthand of writing a cross product because we can write a cross product of vectors by using this epsilon ijk thing. And so what we finally get out of this weirdness is something that even looks more weirdness. Looks like this. So here we go. So that integral becomes this. Minus 1/2 x vector crossed with the integral of x prime crossed with, well, that now. Here. So there we are. We'll pick this up Wednesday. Okay.
Gotcha.
All right. Thank you, Professor.
You're welcome.
All right, bye.
Bye bye.
Good night. See ya.
Good night. I'll try to sleep.
Bye.
Bye.
Take it easy, Professor.
Take it easy.